The goal of exercise 6 is to explore the addition rule of matrix rank. So here I'm rewriting the rule again. So the rank of the sum of two matrices, you don't necessarily know what this rank is going to be, even if you know the ranks of A and B, because the rank of the summed matrix will depend on the elements in this summed matrix. But we are able to set some boundaries. So the maximum possible rank of matrix A plus B is less than or equal to the rank of A plus the rank of B. And of course, this is subject to other constraints like the size of the matrix, the sizes of the matrices, and so on. So this provides an upper bound of the rank of the summed matrix. So what you want to do here is create matrices, so create pairs of rank 1 matrices such that when you add them together, the result, the rank of the sum of A plus B is 0, and then two different matrices such that the result has rank 1 and the result has rank 2. Now, you don't need to generate random matrices and do some weird things. You can just sit down and think about how to create some matrices. They don't need to be random. They can be matrices where you define each individual element of the matrices. And yeah, I hope you find this to be enlightening. You can do it again with matrix multiplication, but actually I'm going to talk in a moment about how that's basically already solved by the previous exercise. Okay, so now I will switch to Python. I'll show you the matrices that I came up with. So for starters, the first part of this exercise was to have two rank 1 matrices that have a summed matrix that has a rank of 0. So what I did was create square matrices where I define the diagonals to be basically all zeros except for one element has a 1 and one element has a -1. So let me just print these out. So here is matrix A. You can see it's the zeros matrix except for the first element is 1. And here is B. Again, it's all zeros except for -1. And now when we add these together, of course, we're going to get the zeros matrix. And so now we can print out the ranks of these matrices. So the rank of A is 1, the rank of A is 2, and the rank of B is 0. Okay, so then I create another matrix where, or another pair of matrices where the sum is rank 1. And so I start off creating A in exactly the same way. And now I create B to be the zeros matrix, but then I change one value. So again, let me show you what this looks like. Okay, well, I don't really need to show you A. I've already shown you that. Now here is matrix B, and you can see that the second number, so the element in the second column of the first row is 10. So what does that mean for matrix C? Well, it means there's going to be a 1 here and a 10 over here. And that means that we can express the second column as a multiple of the first column. So, the second column is 10 times the first column. So that means that although there are two elements in this matrix, the rank is actually still going to be 1. Okay, so in other words, we have constructed an example where we have two matrices, both with rank 1, and the sum is rank 1. Okay, and then here, I think this is the easiest one, particularly once you've seen these two examples already, then we sum two rank 1 matrices together to get a rank of 2. And I guess I can show you what this looks like here. Okay, so here's what the sum matrix looks like. Obviously, it has a rank of 2. Okay, so yeah, then this code is just to highlight something that or I should say empirically demonstrate something that I discussed in this chapter, which is that one of the nice things about working with random matrices is that they will generally always have their maximum possible rank. That's not trivially the case. It depends on the random numbers that you are using. But if you have floating point random numbers generated from some continuous distribution, you can assume that the random matrices will have their maximum possible rank. So the maximum possible rank here is going to be 2. So here I'm again printing out the rank of A and the rank of B and the rank of C. Yeah, this is consistent with the formula that I showed in the exercise text and also explained earlier in the chapter. So, we can change this to 2. We can make this be a 5 by 5 matrix of rank 2, and this is a 5 by 5 matrix of rank 1. And then we see that the rank of the summed matrix is 3, which is consistent with the addition rule of being less than or equal to the sum of the ranks of the individual matrices. And, like in the previous exercise, we can set this to be uh, uh, 20. So I can set the inner dimensions to be 20, but the rank cannot possibly be greater than 5. The rank of this matrix, V, cannot be greater than 5 because it's constrained by the size of the matrix. And that means that if we would sum A and B together, then C is going to be a 5 by 5 matrix, but the sum of the rank of A and B is going to be, 6, because this is a rank 1 matrix, this is a rank 5 matrix. So you sum 1 and 5 together, that is 6. But C is a 5 by 5 matrix. It cannot possibly have a rank of 6. So it's going to have its maximum possible rank, which is 5.